So snow load is a very particular thing because it's actually projected loads. And if you can see this here, so there are these dashed dotted lines here, if you will, that signify that the snow load here is actually acting over lengths of 3 meters, but is actually projected down onto the rafter. And that is a little bit tricky for a beginner, but we will break that down right now. And to make our life easy or comparable, we will use 500 Newton per meter for the snow load as well. And let me just clarify, for educational reasons, I put a little gap here to make sure that we understand that there's something acting on the left and on the right, and it's not like, there's no continuation from left to right, but in reality, no engineer would take the time to break this up. You would just draw a solid line throughout here, and you would look at it as 500 newtons per meter. Let us talk real quick about snow loads as a concept, and let's understand that it is actually projected loads. So we call that due to projected loads. And that, of course, is mostly snow, which, of course, acts towards the center of the Earth as well, but it actually acts along the footprint or the projection. So the projection or footprint. What do I mean by that? I mean that the 500 Newton per meter is acting here over a length of 3 meters, but think of it as each arrow touching the rafter. So if I try to symbolize that for you or visualize that for you, then we would end up with an arrow down here, an arrow down here, here, and so on and so forth. And so each of these arrows, which originally is acting over a length of 3 meters, has to be brought down to this length of the rafter. So now you may ask yourself, why is this done? Why can I not just use self-weight here? Or why can I not just directly convert this 500 along something along that matches this slope? And the reason for that is very simple. Snow loads are given in big manuals for different elevations across the world, or in this case for the United States. And you may imagine that, for example, Florida has very different snow loads than Colorado, and other states have different snow loads. And in fact, in Colorado, different regions have different snow loads, or different elevations have different snow loads. And because when they create these snow loads, nobody wants to tell you anything about how your roof is pitched, right? Because the architect decides that in a sense, or maybe the engineer. But the snow is always defined based on geographic locations, and so it's always based on the projected footprint that the snow produces. And usually, of course, it's not given in Newton per meter, it's actually given in Newton per square meter or something like that, but I took that out here for the concept of this class. Or I guess in the US it's usually given in pounds per square foot, but an engineer would ultimately convert it into pounds per linear foot so that you could apply it to each individual rafter, if you will. So if you understand that, then all you have to do is convert the snow load to a self-weight, if you will, because you see again that we have pretty much forces that are perpendicular. And maybe I draw this here on the other side. So let's take this arrow. So of course, ultimately, we want something that's perpendicular to the rafter and something that is parallel to the rafter. So that would be here. So we have such a force system, and this would be the parallel component, and this would be the perpendicular component. And once I broke that down, then I'm actually at the same case that I had before. However, let's look at this in more detail. So once again, our system is symmetric, and because it's symmetric, RAY is equal to RBY, no different than before. Similarly, RAX is equal to RBX. And so how much load do we have in total? The entire system has a weight of 500 Newton per meter. Now be careful, multiplied by 3 meters. That's all that comes down, times 2. But each RAY and RAX is also sharing the load, so times 1/2. So this of course cancels out. And that is also equal to RBX. Ultimately, RBX and RAX are equal to 1.5 kilonewton, as that is the load that the snow produces on each side of the roof. So now we have the same problem as before. We have two support reactions, right? RAY, RBY, and we also have RAX and RBX. And RAY and RBY we just calculated. So I actually made a mistake here. Let me fix that. So this is not RBX, it should be RBY. RBY, that's the vertical load. And so now I can calculate RAY, which is pretty much done with a similar method as before. So I take the sum of the moments about the hinge, right? So sum of the moments about the hinge is equal to 0. And the hinge actually is at C, by the way, counterclockwise positive. So 0 is equal to, I start with my unknown, RAX multiplied by 4 meters, which is turning counterclockwise, therefore it's positive. I have my RAY, which I already calculated, 1.5 kilonewton multiplied by 3 meters. And now there's many ways of how you can do this. Well, first of all, let's assign a direction. RAY is turning clockwise, therefore it's negative. But last but not least, I need to include my snow load, which is 0.5 kilonewton per meter. And I have to multiply that by 3 meters. And that lever arm now is 3/2 meters. So let's point towards that. So the 500 here is multiplied by 3 meters. That's the distance here. And the centroid of that is acting right in the center, which happens to be 1.5 meters or 3/2 away from C. Because remember, we're taking the sum of the moments about point C. And last but not least, it's turning counterclockwise, therefore it's positive. And so now I created my full equilibrium equation, which now means that RAX is equal to 4.5 minus 2.25 divided by 4. So ultimately, RAX is equal to 0.562 kilonewton. And that also happens to be equal to RBX. Remember the symmetry. So now we are actually at the same point where we were before. Almost, except remember this part here, this triangle here. We will have to deal with that later again. But the logic is no different than before. We now need to go ahead and turn these forces all into parallel and perpendicular components. In fact, we'll do that next. Let me just repeat real quick for the snow load that it is a projected force because that is dependent on geography and intensity of snowfall, and nobody knows how your roof will be pitched, right? So you can imagine that if you have a flatter roof, you have more snow to withstand per length of rafter, whereas if you have like a steeper pitched roof, you of course have snow that is easier to slide down, or like you hold less of it on there. And so it is different way of looking at loads. But once again, the loads of course point towards the center of the earth, because snow is also affected by gravity. But enough about enough about the snow load itself. Let's now move on to our support reactions. And once again, we do the breakdown of the support reaction, which now I don't have to explain as much in detail. But once again, I will break down the long side to a parallel and perpendicular component. So here's the parallel, here's the perpendicular. Same here, parallel, perpendicular. And just as before, I will assign my angle alpha here, which is here. And then therefore I also have angle alpha here. And if that was too fast for you, please see what we did for the self-weight. We used it there as well. So now I can assign my 3, 4, 5s. So here I have 5. So here I have 5. 5 connects 3 over alpha. So this is 3, this is 4. And again, 5. And alpha connects to 3. And then here I have 4. And so now I can calculate my support reactions. And maybe I will help myself here by adding the support reactions. RAY is equal to 1.5. Whereas RAX is equal to 0.5625. So let's do that. Let's do the math. RAX parallel is equal to RAX multiplied by 3 divided by 5. RAX perpendicular is RAX multiplied by 4 divided by 5. And if you solve these numerically, you find 0.3375 kilonewton and 0.45 kilonewton. Now let's do RAY parallel and RAY perpendicular. And that is very similar again. RAY times 4 over 5 and RAY times 3 over 5. No different from what we did for the self-weight. But if you plug in the numbers, then you will find that we're looking at 1.2 kilonewton and 0.9 kilonewton. So that was the breakdown of the support reactions, which now I'm a little bit faster here because we talked about it in the self-weight. So I can move on now to do the same thing that I did before, right? Remember that we now need to combine the perpendicular components and we need to combine the parallel components to end up with an easier calculatable system. So let's move on to the next page. So I collect all my components, and if I do that, then I will find that RAY, or I guess I should call it RA parallel, is actually equal to RAY parallel plus RAX parallel. And that happens to be 1.537. For RA perpendicular, I have to be careful because they are subtractive once again. So I start out with RAY perpendicular minus RAX x perpendicular. And if you plug in those values, then you will end up with 0.45 kilonewton. But just like self-weight, we now have the problem that the snow load also has parallel and perpendicular components, and I will sketch that for you. So we cannot deal with only the force that is going down. We also need to break that down into parts that are parallel and parts that are perpendicular. And so once again, we will break it down for us. And I believe that has already been shown here in this picture on the bottom. So here's my 5, 4, 3 triangle. And of course, you would have to usually figure that out yourself, the 5, 4, 3, but I showed you already how that's done and where to find the connecting angle. So snow load has components that are parallel and perpendicular as well. And I need to consider that now. So let's look at it. Let's start with the normal force again. So for the normal force, I am looking at RAX parallel, and this normal force here, I already brought in the internal forces from my note card. So plus NAX plus 1.5375. But now I need to subtract this component here, the 4 component of the 500. So let's look at it. So 0.5 kilonewton per meter multiplied by x meters. And again, now we have to be very careful because the x is actually acting in this direction, right? So, and the 500 is just not given in that direction. So I actually have to consider what I call the footprint, right? So I have 0.5 times x meters, and now I need to multiply that by the footprint, which is actually given here. So this is 3, right? So it's the 3 side of this 5. So x is actually 5 long when the footprint is 3 long. So therefore, I'm multiplying this by 3 and dividing it by 5. And that makes perfect sense, right? Because x is always longer than the horizontal. And so this number here makes it always a smaller number because the x is longer. So that's my footprint. But I also need to consider that it's only this component, the parallel component. So I'm not getting away with only this. This is the footprint. In fact, I probably should write this down. So footprint. But I need to get the parallel component. So the parallel component would be 4 divided by 5. So that's the parallel component. And that is, of course, a little bit tricky if you never thought about it, but conceptually not different than anything we've done before. So you can now rearrange this equation, and if you do so, you will end up with 0.24x minus 1.5375. And the whole thing in kilonewton. And that is our normal function. The trick here for the normal function, once again, is to understand that x is actually going along the axis of the member, but the 500 is not given along the axis of the member. So that's a little bit tricky, and that's why we use the footprint up here. And then the second part is that we need to only worry about the parallel component and nothing else. And the parallel component of the 500 is defined in this case by the 4. So now that we have the normal force function, we can do something very similar for the shear force function. And of course, the shear force function is everything perpendicular. So you see we have to consider this and this component. And of course, our x needs to be properly considered. So first of all, the sum of the forces in y is equal to 0. Shear force is going down, therefore it's negative, down relative to the reference fiber. 0.45 is going up, therefore it's positive. And now I need to subtract this part. So first of all, it's minus. And then I guess I can just start with the 0.5 kilonewton per meter. And I multiply that by x. But x, once again, is going along the axis of the beam. So I need to get the footprint, because the 500 is actually along the footprint. So times 3/5, once again, footprint. And then I need to get the perpendicular component, which is also 3/5. So this is the perpendicular component. So very similar to before, except the other direction, so 90° to the normal force. If I solve this equation, it actually turns out to be negative 0.18x plus 0.45 kilonewton. And now I can move on to the bending moment, which of course is the integration of the shear force. So we can use the same logic there again. Let's do that. So counterclockwise positive, as always. And I already have included my moment here, which is turning counterclockwise. Therefore, it's positive, positive. I have 0.45, which is this force here, times x, right? Because the lever arm, we're turning about this point here again, and x starts here. And so the longer that gets, the longer x gets. And now we need to worry about this component times x. So let's look into that. We need first to create our resultant force, which is very similar to what we did for the shear force. So 0.5 kilonewton per meter multiplied by x meters multiplied by 3/5. And that is similar to what we have done before. We also need to have this is the footprint. And so this entire thing here actually happens to be the resultant force. So that's the resultant force in terms of x. And so now we need a lever arm, right? And the lever arm also must be dependent on x. So x in meters, but again, x is along the beam, but we need only the footprint of that. So times 3/5. And now times 1/2, because the lever arm is always acting in that half distance. So this is the lever. And that is same logic, a little bit further extended. So it might not be easy to digest immediately, but that's the good thing about these videos. You can just go back and see if you understand the shear force. And if you understand the shear force, then the moment should become clear as well. So now I can solve the equation and get my m of x. And my m of x in this case happens to be negative 0.09 x squared plus 0.45 x. And that equation is in kilonewton meters. And that is good because it's the derivative of the integration of the shear force function, so that matches. And if I plug in 0 for those x's, then I end up with 0. So let's recap before we move on real quick. So for the normal force, we needed to turn the snow load into its footprint through the 3/5, right? So that is because this 3 here is really what we're looking at, like how much we need of the 500. We don't need 500 per meter. We only need the part that is 5/3. And then we also only needed the parallel component because we were talking about the normal force. Very similar for the shear force. For the shear force, we needed the perpendicular component. So that is this part here. But again, instead of 500 per meter, so if x is a meter long, this 500 is actually shorter, or the horizontal distance is actually shorter of the 500 Newton per meter. So therefore we use the footprint. And again, this logic is just extended for the moment calculation, where we used pretty much the same first component here. But then, because we are dealing with the moment, we can just take the sum of the moments about that point, which that, of course, is x times half. Because if this distance, the 500 Newton per meter, is half, then this distance x is half as well. Or in other words, if you take the middle of 3 and this being 5, so then you have the middle of 3 and the middle of 5, they both would act at the same distance. And that's how you can take advantage of that in this equation here. So that concludes our equations, and we can now move on to drawing the internal force diagrams. So what I will do next is I will just bring over my equations. So for the normal force equation, I used n of x being equal to 0.24x minus 1.5375, if I'm not mistaken. And it's very similar as we had before, right? So first of all, it's also in kilonewton, but also it's compression throughout the entire roof, and it's increasing towards the bottom. Of the roof, and then it's also not zero at the top because we have the pitch of the roof due to the angle. So that hasn't changed. In fact, if you paid very close attention, you see that this equation, except that the numbers are a little bit different, but the concept of the equation is the same as we had for the self-weight. And this is on purpose here for educational reasons, right? I used the 500 and the 500. Actually, any value would have made the form of the equation the same, no matter what I would have chosen. But since we used 500 for snow load and 500 for self-weight, you see that here for snow load, you actually end up with smaller factors now. And that is because the snow load is distributed over the footprint, and the self-weight actually was acting over the entire length of the beam, so that made that more intense. But I can now draw the normal force diagram just like I drew it before. The concept is the same, and if you don't know, you just plug in your values, but you know this from the self-weight case that it must be linear, it must be increasing towards the bottom. So it looks like this. And while I'm at it, I will do the very same for the other side. 90-degree angles, of course, for those lines. And both are negative because it's compression, compression, compression. And up here I have this. And last but not least, I need my values, which of course here on the bottom is minus 1.5375 0.375, and that is here and here. And on the top, I can just plug in x equals to 5, and if I do that, then I will end up with negative 0.3375. Not to forget my identity here in kilonewton, and that is the normal force. I don't think I have to explain much here because it's literally the same thing as we had for the self-weight, except with different values because our equations are a little bit different. Same is true for our shear force. It will be also in kilonewton as before, and we have a shear force function as v of x, which we calculated to be minus 0.18x plus 0.45 kilonewton. And remember that we had a symmetric system, and therefore our shear force is anti-symmetric. And needless to say that the shear force is equal to 0 at x equals to 2.5 meters. So we need that for the moment. But let's look at this before we draw, before we go to the moment. So I will just draw it. But first, notice here that we'll start off with negative x, which if I put 0 in here, then I end up with positive 0.45. So that means here is the left side, and I have to go up, right? Because I have to follow my arrows here. And then I go down, 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 down with a linear function as I show here. So when I want to draw that, it's going to look something like this. There's my positive value. And if I plug in 5 for x into my equation, I will find that it's actually going to negative 0.45. So what I will end up with is a linear function that goes from positive 0.45 to negative 0.45. And now it's anti-symmetric, keep that in mind, right? But everything else stays the same. The logic stays the same, and when in doubt, you just can solve or analyze the support B and then draw the internal forces for that direction. But we already know how it looks like from previous analysis. So here it's positive now, and here it's negative, with of course the same values, minus 0.45 and plus 0.45. So with that said, I can move on to my moment diagram. Just as before and as always, I can bring down my maximum / minimum values, or like where my values will be maximum or minimum. And so I have that intersection there and this intersection. And my moment diagram will be fairly simple to draw now, because I know it's 0, I know it's 0, I know it's 0. And remember that snow is also attracted by gravity, just like the self-weight. And therefore, I don't have to change my logic of the beam is smiling or frowning. In fact, it's smiling. Therefore, I must end up with a maximum and a maximum on both sides. And therefore, I have functions that look like this, where there's my maximum in the middle and my moments are positive, positive, and positive right there. So now I'm done. Of course, I still need to calculate my maximum value, but what's easier than calculating a maximum value if you know where it is and if you have a function? Remember that the function was m of x being equal to minus 0.09x squared plus 0.45x. And this, of course, in kilonewton meter. And so if I set my if I want to find my maximum bending at x equals to 2.5 meters, and I plug that in, then I find m max, which actually happens to be 0.563. And of course in kilonewton meter. In fact, I need to show this here, what my graph is. Kilonewton meters. And here is no different, plus 0.563. And that concludes my moment diagram. So let's take a look, and maybe for completeness, where V is equal to 0. And of course I have positive bending all the way through. So throughout, because think about it, the snow is just a different way of self-weight on the system. I mean, it's not self-weight, but it acts like self-weight because both of them are actually attracted to the center of Earth, which, by the way, will be different for the next case we're going to talk about, which is wind load. But I will talk about that in a second. Before we do that, let us discuss these again. So normal force increasing downwards, and like every piece of snow adds more and more and more weight here until it's supported. And so this graph makes perfect sense. Shear force diagram has to be linear because effectively there's an evenly distributed force acting on the roof. And because it's a symmetric system, the shear force must be anti-symmetric with a zero pass-through at the middle of the members. And that means that for our moment diagram, we must have a maximum here at the center of the beam, which we calculated simply by plugging in 2.5 to these equations. So these equations can be a blessing, if you will. And with that done, I think we are ready to finalize or pretty much put the internal force diagrams for snow load to rest, and we move on to wind loads.